Initially, there was an infinitely dense mass of matter. This mass underwent an explosion that gave rise to the formation of atoms, molecules, stars, and galaxies that we can observe today. For decades, this has been the explanation offered by physicists. However, recent research has introduced a new perspective that suggests the universe does not have as early an origin as initially believed. Instead, it may be part of a cyclical process in which the universe goes through a series of cycles of expansion and contraction, possibly in an infinite loop. Brian Cox, a renowned physicist, has also raised doubts about the Big Bang theory, arguing that something cannot arise out of nothing. This questioning adds an intriguing element to the discussion. In addition, research from the James Webb telescope has revealed information that contradicts the idea that the Big Bang marked the absolute beginning of the universe. This leads to the fundamental question: if the Big Bang was not the beginning of the cosmos, then what was? Join us on this journey to the beginnings of the cosmos, where we will explore the frontiers of the Big Bang and answer this question and many more. If you are interested in keeping up to date with news about the universe and its surroundings, subscribe to our channel, hit the like button, share this video to reach more people, and turn on the notification bell. Scientists have developed a detailed understanding of the universe in its earliest stages, known as the Big Bang theory. According to this model, the universe was much smaller, hotter, and denser than it is today, approximately 13.8 billion years ago. During that period, all the elements that make up our world were formed in a matter of minutes. In this theory, our universe, including stars and galaxies, was once as tiny as a peach and had an extremely high temperature of over a quadrillion degrees. Interestingly, this astonishing narrative aligns consistently with all current observations. Astronomers have investigated everything from the remnant electromagnetic radiation of the early universe to the abundance of the lightest elements and have found that everything agrees with the predictions of the Big Bang. To the best of our knowledge, this description fits the reality of our universe perfectly. However, despite its apparent robustness, we know that the Big Bang theory is not the complete picture. There's a missing piece to this puzzle, and that piece is an understanding of the first moments of the universe. This challenge is due in large part to the limitations of the physical theories we currently employ. The combination of general relativity and high-energy particle physics provides us with a valuable conceptual framework. However, as we delve deeper into the initial moments of the cosmos, the mathematical complexity increases significantly, reaching a point where our current methods cannot provide meaningful solutions. One of the indications of this difficulty is the existence of a singularity, a point of infinite density at the beginning of the Big Bang. This notion suggests literally that the universe was once compressed into an infinitely small and dense state, which seems to be absurd. To address this challenge, we need to explore new frontiers in physics, develop an approach that overcomes these limitations, and provide a more complete understanding of the first instance of the universe. Our current instruments and theoretical frameworks are not robust enough to address this challenge, so we need to develop new physics that can encompass and explain gravity and the other fundamental forces at extremely high energy. This is precisely where string theory comes into the picture. This theory aspires to be a physical model capable of unifying gravity with the other fundamental forces, especially at ultra-high energies. In essence, string theory posits that it can provide an explanation for the first moments of the universe. Within string theory arises the concept of an ekpyrotic universe, which takes its name from the Greek word meaning a configuration or a fire. This idea suggests that the Big Bang, as we know it, was the result of an earlier event, implying that it was not the absolute beginning but rather a part of an ongoing process. Extending the notion of an ekpyrotic universe has led to the development of a related theory called cyclic cosmology. Although the idea of a cyclic universe has been considered for millennia, string theory provides a solid mathematical basis for this conception. In the framework of cyclic cosmology, the universe functions as if it perpetually oscillates between large explosions and collapses in an endless cycle that extends infinitely into the past and future. This theory of cyclic cosmology was proposed by the eminent physicist Roger Penrose, who was awarded the Nobel Prize. Penrose was intrigued by a remarkable mathematical relationship between the early universe, characterized by extreme density, heat, and smallness during the Big Bang, and the future state of the universe, which is characterized as extremely cold, expanded, and devoid of matter. The theory suggests that these two states become mathematically identical when pushed to extreme limits. Although it may seem paradoxical, the total absence of matter could be the driving force behind the creation of all the matter we observe in the universe. From this perspective, the Big Bang originates from what remains almost imperceptibly after all the matter in the universe has been consumed by black holes that eventually evaporate into scattered photons in a vast void. the universe emerges from what, from another point of view, essentially approaches nothingness. Although this nothing is still a form of something that constitutes a physical universe, albeit an empty one, the mystery lies in how the same state can be interpreted as both a cold, empty universe and a dense universe, depending on the point of view. The key to this understanding lies in a complex mathematical technique called the conformal transformation, which is a geometric transformation that changes the size of an object while retaining its shape. Roger Penrose showed that the empty state and the hot, dense state can be connected through this scale transformation, aligning their spatiotemporal structures despite their differences in size. However, Penrose argues that the concept of size loses its relevance under these extreme physical conditions. In cyclic cosmology, the sequence of events unfolds from an old cold state to a young hot state. The presence of the hot and dense state is the result of the previous cold and empty state. However, this causal relationship does not follow the usual pattern in terms of time since, in these extreme states, both size and time lose their conventional meanings. The cold, empty state and the hot, dense state exist on separate timelines, which means that, from the perspective of an observer within his own time frame, the cold, empty state would continue indefinitely. Physics and philosophy are intertwined in this realm of cyclic cosmology concepts. Cosmology provides speculative and detailed explanations for the origin of these cycles. However, even if Penrose's ideas gain support in cosmological advances, a deeper philosophical question still lingers about the origin of physical reality itself. How did these cycles come into existence? This leads us to ponder the reason for the existence of something rather than nothing, which is one of the fundamental metaphysical questions. For our purposes of discussion, we will focus on explanations within the realm of physics, and there are three possibilities to consider in exploring the origins of these cycles. First, there may be no physical explanation at all. Second, there could be an infinite series of cycles where each cycle represents a different universe, and the initial quantum state of each universe is somehow determined by some aspect of the universe that preceded it. Finally,